Hello everyone, welcome back to one more question from organic chemistry. This question is about saccharine. We have known this is used as artificial sweetening agent, and this is very sweet in taste in comparison to our normal table sugar what we are using as a sweetening agent. This is nearly 500 times sweeter. That's the structure of our saccharine molecule. And in actual saccharine molecule, there is one hydrogen atom present, and that gives us relatively lower solubility. When we are replacing this hydrogen atom by sodium or calcium, then this becomes very much highly water soluble. We know because salts are relatively more soluble because of increased interaction with the water molecules. So here we go about the main question which we are having. Then we'll come back to some few more facts about the saccharine, how it is, and what are other implications. Now, this question is a single option correct question, paragraph based. So the paragraph given to us is toluene is being reacted with chlorosulfonic acid. This is chlorosulfonic acid, and we are getting now two products formed, P and Q. This reaction would be having some nature of electrophilic aromatic substitution we could possibly anticipate, because chlorosulfonic acid can possibly be generating some electrophile. So out of these two, because CH3 group was going to have its plus H effect, so we expect this is going to be ortho and para directing. So that is our clue over here. We can think that way. Now the compound P, either ortho or para, we'll be discovering it maybe later. This is being reacted with NH3 ammonia. So then we are getting some compound R being formed. This compound is being reacted with alkaline KMnO4 and followed by acidic medium. There would be one clue. Alkaline KMnO4, when we were reacting, the side chain oxidation was supposed to be happening. So what we anticipate in compound number S, when it was formed from R, there would have been side chain oxidation. So CH3 must have been converted into carboxylic acid group in this particular step. And ammonia has been reacted in the previous step, this thing. So we have to read from here. If ammonia is being reacted in the previous step, carboxylic acid is being generated in this particular step, where this ammonia is reacting with. Ammonia must be reacting with over here, which is either sulfonic acid group, that is SO3H, which can be coming from here, or it can be reacting with SO2Cl, sulfonyl chloride. That we have to figure it out. We'll be doing that in a moment. And then this compound number S, where there is one carboxylic acid group and there is one, definitely this R group, R compound must be having one sulfonamide group, that is SO2NO2 is here. This compound number P is having SO3H present or SO2Cl present, that we can discover in a moment. So compound number R is having one SO2NH2 group and one CH3 present, that's for sure. And compound number S is having now two things, one carboxylic acid group coming from here and one SONH2 group coming from the reaction of this thing and ammonia. Now when we are heating that compound, we are getting some compound called saccharine. Now we are expected to know the structure of saccharine. This is there in our books as the chemistry in everyday life. The structure of this compound is, we have got sulfur. This is basically some sulfonamide derivative. This is the structure of saccharine. So what would be happening in this particular step? It is easier to think now in this heating step that carboxylic acid group and the sulfonamide group must be reacting, and there would be a dehydration, basically kind of loss of water is happening, where the NH2 can be attacking to the carboxylic acid and one H and one OH will be lost. So this is the paragraph given. Now we should be going further and we'll be trying to see how that P and Q are being formed and what are the rest of these steps one by one. And then we'll be going back to the questions. What two questions were asked on this paragraph? So the first step, what we have seen, this is going to be electrophilic aromatic substitution, where the hydrogen atom of the benzene ring is being substituted by SO2Cl, and that can be happening at ortho and para position, because the CH3 group we know used to be ortho and para directing. So we are having two possibilities. One, we are getting SO2Cl at the ortho position. Another one, we are having it at para position. Now the question was whether SO2Cl would be coming or SO3H would be coming onto our benzene ring. For that, we need to go a little one step back because we need to see how the electrophile is being generated. This is our chlorosulfonic acid over here, and because this is quite acidic, there may be some H plus ions coming from another such chlorosulfonic acid molecule. Now another H plus molecule is difficult to attack on chlorine. This is going to attack definitely onto the lone pair of oxygen, which is relatively more electron rich and which can be easily protonated. If that is happening, we are getting protonated OH group present, which can be lost. If this group is being lost, sulfur is getting a positive charge. That is our electrophile. So SO2Cl, sulfur bearing positive charge, is our electrophile. Water molecule has been lost in the very first step during the generation of electrophile. Okay. So basically that electrophile will be attacking over here, that SO2Cl with a positive charge would be attacking onto this benzene ring, and because of its interactive influence, it can be coming onto this ortho position or it can be going onto the para position. So P and Q were two of the products. With the first step of reaction, we don't know which one is ortho, which one is para. That is coming from the second sequence of reactions which were given P, R, S, and then finally saccharine. Because saccharine can be generated only from the ortho position, that means the compound P, what we must have started, it must be the ortho derivative, right? So here the second step, when this compound number P was reacted with ammonia, this was nucleophilic acyl substitution of the chlorine over here by one NH2. It is just like the acid chloride reacting with ammonia as giving you acetamide. Just like that, the sulfonyl chloride reacting with ammonia is giving you sulfonamide. That's the reaction. So compound number R was orthotoluene, orthomethyl benzene sulfonide, or we can say orthotoluene sulfonamide. Now the side chain oxidation comes over here. Alkaline KMnO4 will be converting that side chain into carboxylate COO because reaction medium is basic. Then we need acidification. So acidification further will be giving you benzoic acid. That is your compound number S over here. This is carboxylic acid and this is sulfonamide. And now when we are heating it, this is going to be, we can visualize this as the loss of water, but this mechanistically would be happening by the attack of lone pair of nitrogen onto the carboxylic acid. OH will be lost from the carboxylic acid group, H plus will be lost from the NH2, and then we are getting this thing. Saccharine is water insoluble. Rather than saying insoluble, we should say sparingly soluble. Its density is very, very less. We'll be seeing that data in a moment in comparison to this sodium salt, which is going to have much higher solubility. So what we do, because this hydrogen is very much acidic, because negative charge can be resonance stabilized onto 3 oxygens, carbonyl oxygen as well sulfonyl oxygen. So this is going to be saccharine sodium, which we are using in different applications. This is going to be highly water soluble. Again, we'll be seeing the data in some time. This is supposed to be providing no calories, and that's why we are using this. We have been actually using this as the artificial sweetening agent in different food products. So those were the different set of reactions. Our given question did not deal with this thing. Our question was till this particular point where saccharine was being formed. Now we'll revisit the question, what were asked. So the first question was, these are the set of reactions we have just seen. The first question was, choose the incorrect statement. Please note that they did not ask the correct, they asked the incorrect statement. So first statement is, P and Q are obtained from the toluene by electrophilic substitution reaction. That is true because we have seen this was the, we have written here, this is electrophilic aromatic substitution. This was ES, this is true statement. Because this is true statement, this is not the correct answer because we are asked about the incorrect statement. Second option says SO3H will get substituted on the benzene in the first step, and product formed is paramethyl benzene sulfonic acid and orthomethyl benzene sulfonic acid. That is not happening. See, we talked about over there that the electrophile generated was SO2Cl plus, so this will be getting substituted and not the sulfonic acid. So this is false statement, and we were asked about the incorrect one, so this is going to be our correct answer. Now in option C, they said P and Q are positional isomers. True, because they were ortho and para, which are going to be the position isomers, and SO2Cl will get substituted in the very first step. That is also a true statement. That's not going to be a correct answer. So the correct answer to this first question of this paragraph was, in the single option correct, it was option number B. That's it. Now the second question on the same paragraph was over here. These are the same reactions. So the second question was, now they asked about what is the correct option. So P is the orthoisomer. Of course, we know, because saccharine we can get from the orthoisomer only, and because they started with the P only over here, so this is going to be the correct option. Q is the orthoisomer. No, that's not the correct answer. Number of oxygen atoms in SR3. Our compound number S was this thing, the carboxysulfonamide. Over here, we are having 2 oxygens in carboxylic acid and 2 oxygen in sulfonamide group. So it was not 3, it was 4. So that was also incorrect. Number of sp2 hybrid carbon atoms in the saccharine are 6. In saccharine molecule, you are having all the benzene ring carbons, which are sp3 hybridized. So there are 6 carbons over there. Then there is 7th carbon, which is sp2 hybridized. So they asked only about the carbon atoms. Sulfur, nitrogen and all they are not saying, so this was not 6, this was actually 7. So that was the question about the saccharine. Now some more related things we may require to discuss, which may be possibly useful in the further questions, maybe sometimes later. Okay, here we go. So saccharine has been actually used in the forms of sodium saccharine only. We were talking about the solubility of the sodium salt is very, very high. And we are using sodium saccharine because saccharine as such is having very less solubility, and solubility is 3.5 grams per liter. So saccharine as such without any salt formation is dissolving 3.5 gram in 1 liter. That is very, very low solubility. And if you talk about the sodium saccharine, in 1 liter we can dissolve 670 gram. That is a huge difference, and that's why we are using this as the sodium salt. Actually, similar situation we had seen earlier when we were talking about the aspirin versus dispirin. Dispirin we knew that used to be the calcium salt, which we have used as dispersible tablets, which are dissolving in water very easily when you are putting in a glass of water. And aspirin, on the other hand, was not any salt, that was just the acetyl group and carboxylic acid group that was having relatively less solubility, comparable to what we are having in the benzoic acid. Okay, now this is an artificial sweetener, and because this does not belong to the category of the carbohydrate which our body can metabolize, so this is supposed to be having 0 nutritional value. Like if you consume saccharine, you'll be getting 0 calories out of it, because our body is not going to digest it, does not know how to process this molecule. Our body has not been designed for that kind of molecules actually. And it is about 550 times as sweet as sucrose. The data actually changes from different sources. We don't have the exact calibration that can be done using different methods, so we can say this is about 500 or 550 times as sweet as our table sugar sucrose is. And this is also having bitter metallic aftertaste, so when you are consuming it, then after that you'll be getting some bitter taste remaining afterward. That may be the reason we have seen in Diet Coke and a number of similar products which are going to give you some different kind of weird taste after consuming those products. This is actually also used in consumptions of not just cool drinks, some candies, some cookies, and a number of medicines which in particular kids don't like. For them, saccharine has been used as sweetening agent so that they can easily take those medicines. Okay, then there have been some implications of these saccharine. People have been a little bit skeptic about the use of the saccharine, and whenever this is used as food additive, there are some codes. If you have ever observed, those food products are having some food preservatives or different additives added, and they are using with some E codes. So if that saccharine is present in some of the food product, it should be E954. Also, the effects, or you can say side effect, have been controversial. We did not have the straightforward answer. Few people are still believing that saccharine is not safe at all. This has been proven to be carcinogenic, and some people say this is going to be relatively safer. There are different opinions. We can hardly do about that, but this is some walkthrough from what happened to the saccharine, how people responded across different years. So 1879 this was first produced, and then some patents and all start coming in 1884, and after that its production started across Europe and different places. And then it was World War II when sugar supply got shortage. So when sugar supply got shortage, people needed something for their sweet products, so then saccharine set into the use. And 1985 FDA did not allow it to be used as such because of those reports, because our saccharine was not supposed to be safe as to be used. Later some of those different food companies, or the companies which were branding or which were using doing production of the saccharine, they suggested some data, and FDA approved its use in 1977, but there were some warning signs that this can be potentially not this can be potentially harmful, that warning signs they gave. And then again debate started, and a number of famous people have appeared in and against for the use of saccharine in the food products. Later in 2000, FDA removed those warning labels. Some environmental protection agencies also came in the support of FDA, and they declared that this is going to be safe for the human consumption. And now this was mostly about the FDA and all. Now coming back to India, we have got FDA, FSSAI, that is Food Safety and those association, which is governing basically the food products and all. What are the rules and regulations governing those food products? They say that the sodium saccharine, which is the sodium salt, which is soluble, is recommended for use, and they also say this is going to be safe. They give the reference to the number of different countries which have done research and which have published their results. They say they believe it is very, very safe. But they have set the maximum permitted levels which can be used across different products. And people from India which use too much of the pan masala things, they should be very much aware that pan masala is something which is having very, very high concentration of sodium saccharine, which they may be believing is coming because of some sweet thing present over there. And to be very much frank, people from India hardly bother about whether there is a saccharine present or something else present. But why I am trying to correlate the number of different people suffering from mouth cancer which are consuming too much of the pan masala may possibly be, I do not imply this is definitely the thing, but that may somehow be related with the overconsumption of pan masala, which contains lot of saccharine in it. You see number of different products, they are having relatively smaller amounts. And if you are a kid, which I believe most of my audience can be the age group of, which are very much into the chewing gum kind of thing, I have seen people in my class as well. So that is also going to be actually very higher side of the saccharine. And that although these different agencies, FDA and FSSAI, are saying is relatively safe, how much is that how much safe and how much exposure that can be safe, that is again something which I cannot comment upon, but I definitely would say use with caution. Okay, I think that's all in this question and this discussion about the saccharine. That's all for now. Thank you. Bye-bye. I hope we learned few things, and not just in hardcore chemistry about the questions which we have done. Few things related to our chemistry in everyday life as well. That's all for now. Stay tuned for more updates, more such questions actually. And this is the thing which I found somewhere. You can just have a look. That's all for now. Thank you. Bye-bye. Stay tuned. Keep supporting the channel by liking and subscribing. See you next time.